Yeah, comes on everyone. Let's start off. The last thing that we did, we talked about current density. Great. Now let's go ahead, a bit of a theory. Now, if you look at the electrons inside a conductor, so first let's see what happens. How does electrons actually behave inside a conductor? So we define something called drift velocity. So if you just look at an electron inside a conductor, they're just moving randomly in all directions. So the electron is moving randomly. That's because of collisions between them. This is also called as Brownian motion. If you remember, this we discussed in KTG, kinetic theory of gases. This is how the molecules also, they keep moving randomly in all directions. So if you don't apply any electric field, these free electrons are moving in random directions due to collisions. Others do keep your cams on. This is called as Brownian motion. And because they're moving randomly, the displacement will be zero. So we get V average is zero. That means these things will are never responsible for current. So that electron is always almost in the same place. It is just moving in that same locality. So charge will not flow, in forward or backward direction. So there is no current. So it does not result in current. And if you actually try to calculate this speed, so this is thermal kinetic energy. If you remember, this is equal to 3/2 kT. K is the Boltzmann constant, which is equal to half mv thermal square. So this speed is called V thermal because this is coming due to temperature. And this speed is very high. So these electrons inside the conductor are moving in the range of 10 power 5 to 10 power 6 meters per second. So these electrons are moving very fast, but they don't create any current because they're moving randomly. So that is the thing. So you have a lot of energy, but you're doing all random stuff. So it just goes to waste. So it does not result in any net flow. Clear with this? So if you just put a conductor there, this is what happens inside. What happens if you apply a voltage now? Now, if you apply a voltage, let's say we put a battery here. Let the voltage be V and let the length be L. Now the field inside will be E is equal to V by L. So there will be an electric field inside where E is equal to potential difference by distance L. And then because of this, the electrons will start going in the opposite direction. The force will be this way. F is equal to EE. So this will result in a systematic motion. So this force will move the electrons in a systematic direction. Moves the electrons in a constant way, or it drags the electrons. It drags the electrons along the opposite to the field. Because the electron is negative charge, they go opposite to the field. Now, because of this, what will happen? If you see the net motion, you'll actually see the electrons are having two types of motion. One is the random motion and the systematic motion. So the electron is trying to go randomly. The green is the systematic motion. So this is how it just keeps going on. So we have two types of motion here. Maybe I should put all this in green. So E is equal to V by L. This is E. This is force. And this is your electron. So it's a random motion plus systematic motion. So these electrons experience both the things. So there is a random motion which is coming because of your thermal kinetic energy, which is making you go in random directions. And there is a systematic motion because of the battery. There is a field due to the battery that is dragging you. And this is responsible for current. If I have to give an analogy, think of like this. I said the same thing in, we did have this discussion in KTG once. Think of like this thing, okay? Let's say you're going for, this Ganapati Visarjan. Kabhi dekha? Once the Ganapati festival gets over, we take the, the Murti and we take it for Visarjan. Now, if you see that procession going on, right? If you look at the people around the procession, they're jumping around, they're dancing, they're doing any nonsense, right? Completely random. You cannot even tell what that person is going to do next. They're colliding with each other, they're dancing, throwing colors, they're doing any nonsense. It's completely random. You have no idea what the hell they're doing. But the moment the procession goes from here to here, because the procession is going slowly, the moment procession goes from here to here, the randomness or the random people also move with the procession, isn't it? Now you tell me, no matter how fast that person is running and jumping here, will the procession move because of that? No. But the moment the procession moves, the randomness also moves with it. This is a classic example where a random motion is moving systematically because of the procession. So the person moving is your random thermal energy and the systematic motion is the speed of the procession. So now if I ask you this question, the displacement of the man is what? The displacement of the man is the displacement of the procession, which is going slowly and steadily on the road, isn't it? So that goes very slowly. But whereas the people are actually moving very fast. The procession goes like what? In 1 hour, it might go only 1 kilometer. So it's like an average there. Is this clear, everyone? So that is how you can compare this. So whenever you think what is random, what is systematic, think about that, the procession. That's the best example there. Clear with this? And now going ahead. So we got the length is L. So we know only the systematic motion is responsible for current. Field is equal to V by L. So the electron here will experience a force F. So we get acceleration is equal to field electron ka charge by mass. So from here we get V drift is equal to A into tau. So we define something called tau. What is this tau? Again, this thing comes from KTG. Tau is called relaxation time. So what is relaxation time? This is the average time interval between two consecutive collisions. This should go to the expansion KTG. There. Page 123, mean free path, relaxation time, collision rate. These are the formulas which you should definitely mug up. And mains, they did ask a lot of questions. And if you remember, I showed you the mains questions I asked you also. So this is in page 123, thermal expansion. I will leave the reference there. You can check it out. And what was the formula? Tau is equal to 1 by root 2 pi sigma square NV. Sigma is the diameter, NV is the number of molecules per unit volume, and this is V mean. So sigma was diameter, NV is the number of molecules, or in this case, electrons, by volume, and V mean is root over 8 RT by pi m. All this is coming from KTG. So you can clearly see this tau is proportional to 1 by root temperature. Means if you increase the temperature, electrons will go faster. If they go faster, they'll collide faster. That means the time interval between them will decrease. And we will use that later on, but that's a little discussion about tau. If temperature increases, right, molecules move faster and the collisions increase. Therefore, tau decreases. So that's a little discussion about tau. So we are assuming before you collide with the some other guy, you have an acceleration of a is equal to tau. And now we got v drift here. Now this value of v drift, this is actually very slow. This thing is in the range of 0.1 to 1 centimeter per second. Look at the difference. The thermal speed was going 10 power 5 meters per second. That's 100 kilometers per second. This thing is going 1 centimeter per second. So the drift is very slow. And now if you remember that formula, I is equal to NEAVD. This we did from current electricity, problem 1C. I told you it's an important problem to remember. So if you substitute that formula here, we get I is equal to NEA V drift, where N is the number of electrons per unit volume, E is the charge, and A is the area, and this is the V drift. Let's go to the next page. But all clear with this. We are going somewhere with this. So let's see the story. I know it's like I'm putting things, but what are we doing exactly? You will see. So we get I is equal to NEA V drift, and V drift is nothing but NEA acceleration. Acceleration is EE by M into tau. So this can be written as NE square tau by M area, and E is nothing but V by L. So I can write this thing as V is equal to M by N E square tau into L by A into I. If you look at this formula, this thing looks like V is equal to IR. This is your Ohm's law. Okay, so dot आना चाहिए. What is dot? M N E square by tau. Are So this thing here is mne square by tau. So this quantity here is V is equal to IR, which was your Ohm's law actually, if you see. So the Ohm's law just didn't come out of thin air. We can actually derive it. And if you see this quantity, we defined rho as resistivity. Okay. Resistivity, which is given by M by N E square tau. M is the mass of electron. N is the number of electrons per unit volume. E is the electron charge, and tau is the relaxation time. And we define this resistance R is equal to rho L by area. I hope you remember this formula. That's your classic resistance ka formula. right? And what is L here? L is the length along the current flow. So be careful. L is not any random length. L is the length along the current. A is the area perpendicular to the current flow. And from here we get V is equal to IR. So this is all that stuff that we got. And we can also define rho is equal to 1 by sigma. That becomes your conductivity. So sigma is 1 by rho. This is defined as conductivity. Inverse of resistivity is conductivity. There. So these are the main stuff. Now that will be important. You know why? Tomorrow they will say like this: in a hypothetical universe, mass of an electron has become double, and the charge of the electron has become tripled. And they'll ask you, what is the resistance of the wire in that universe, and what is the resistance of the wire in our universe? So they'll give you some hypothetical scenario like this. Now, if you get this resistivity rho, mass became double, charge became triple. So that will be 3 square E square. That means it became 2 by 9 times. That means the same material in our universe and their universe, it will be 2 by 9 ka difference. You're getting it? So they can create things like that. Or they can say like this: it is found out the mass of an electron has an error of 0.01% and charge has an error of 0.1%. Find the error in resistivity. I can create resistivity problems with that. Clear with this. So not standard, but who knows? They can do anything. Clear? Still, we can combine more stuff here, and then N will vary with temperature and depends on the material to material. Copper will have more N compared to steel. N is like what? How many free electrons you have? So N does vary with temperature though, and material. So if you look at this formula here, which we got, V is equal to rho L by area into I. I can combine this stuff. So bring that V by L here again. And this will be rho I by area. V by L becomes field. Rho becomes 1 by sigma, and this becomes J. This is J is equal to sigma E bar. This is a very important relation. This is also called as a microscopic Ohm's law. This is actually more powerful than V is equal to IR. Microscopic or vector forms of Ohm's law. Because V is equal to IR if you see all scalars, but this will give the vector form. Or you can say the vector form of Ohm's law. This is actually more powerful than V is equal to IR. We will see questions later on that. So, voltage has nothing to do with it. Voltage will simply make you the drift go, right? That voltage, see, what is a free electron? You have to pull the electron out of the nucleus, isn't it, Arya? Your voltage is not so strong that it will pull the electron out of the nucleus. The electrons are already out. These are all conductors. Clear with this? So J is equal to sigma E. This is something more. Look at how many new formulas are there. V is equal to IR, you already know. Resistivity is this. If you can remember, great. If you can't, that's kind of okay. Means I don't think they'll ask you. This formula you should definitely know. R is equal to rho L by A. If you know rho, you will get 1 by rho. So that is taken care of. J is equal to sigma E. This is another new one. And if you try to plot a graph, voltage versus current, if you get a line passing through the center, then here dV by dr, that's di is resistance. But sometimes you will observe the VI graph is not a linear function. It might be a curve. So in this scenario, we get dV by di is resistance. This is called dynamic resistance, meaning this is a resistance which is varying with current. So you will find materials like this. So if something obeys, this straight line, so materials which obey Ohm's law are called ohmic conductors. So there is no guarantee every time, everything will obey Ohm's law. So all materials need not obey V is equal to IR. So suppose if they give you a graph VI and if it is a curve and they can ask you find the resistance, you actually find the slope. This is called dynamic resistance. So it's a resistance which changes with the current or whatever. Flux of J. We'll see. We'll see. All clear with this? Next thing, if you see a bit of a theory there, this is an important thing. There have been a lot of theoretical questions on this. For conductors, if you increase the temperature, tau decreases. Remember, if you increase the temperature, they'll move faster. So they will collide in a shorter time. So tau decreases. Therefore, resistivity increases. So material will become more resistive. And therefore, resistance increases. So for conductors, if you increase the temperature, resistance increases. But for semiconductors like silicon, carbon, these are all semiconductors. Silicon, carbon, germanium. If you increase the temperature, yeah, tau still decreases, but something more happens. For a semiconductor, the number of free electrons are very less. So when you increase the temperature, more electrons will come out of the lattice and the n increases. So look at this thing formula here. The n is in the denominator. So even though the tau decreases, the n will increase like pretty rapidly, pretty large value. So the number of free electrons increase. It's like this, you don't have enough free carriers. Now you suddenly increase the carrier, so the rho decreases. So for semiconductors, if you increase the temperature, resistance decreases. In case of a conductor, you already have a lot of free electrons. So even if you increase the temperature, the change is negligible. But for semiconductor, it is like you have 10 people carrying your food. Now suddenly there are 100 people. So the percentage change is 10 times more. Even though for a conductor, you get, see, think of like this. For a conductor, there are 1 crore free electrons, 10 power 7. For a semiconductor, there are 10 power 3 free electrons. When you increase the temperature, here maybe 1,000 people will add. Here 1,000 people will add. Even though the number is same, this thing is 100% increase, isn't it? This is a negligible change in percentage. So what matters is the percentage there. So it looks exponential there. So R decreases. This is a very important thing. You should definitely remember this. There have been theoretical questions like this. Do you guys remember in physics, in one more chapter, there is something like this. With increase in temperature, something increases. With increase in temperature, something decreases. Anyone remembers what is that? There is a property something like this. ऐसा ही हुआ था. For some materials it increases, some materials it decreases. नहीं रे यार ये. Right, उत्साह. क्या बोल रहे हो श्रीहरि? What are you even saying?
The coefficient of expansion.
नहीं रे. There's nothing like that. Yeah, right, उत्साह. You got it. Yeah, I'll show you where it is. You guys forgot. First page देख. Viscosity. With increase in temperature, viscosity of liquids decrease, viscosity of gases increase. Remember this. So this is the kind of statement questions you'll get. So we had something like that for this thing. So when you try to find this temperature R of T, this is equal to R naught into 1 plus alpha delta T. Alpha is the property of the material. Alpha linear expansion has nothing to do with it. So this is the resistance at temperature T. So it's a linear function. This thing looks like that linear expansion stuff. Technically, this is actually 1 plus alpha T plus beta D square plus gamma T cube and so on. But we are going to ignore it. For small temperature changes, we can assume it is linear. R naught is resistance at 0 degrees. Alpha is the coefficient of resistance. So sometimes you'll get questions like this, I'll show you one. Easy questions, but yeah, you need to know. Delta T is change in temperature. Basically, it's the temperature from 0 degrees. So until unless they don't mention it, we'll take it to be linear function. So this is one more formula to remember. There are a bunch of formulas. So alpha is negative for semiconductors because when you increase temperature, resistance decreases. So how many formulas we have? V is equal to IR, R is equal to rho L by A. These are the main ones. Rho, like I said, if you can remember, great. If you can't remember, that's also fine. J is equal to sigma E. This is the third one, and R is equal to R naught plus 1 plus alpha delta T. These are the four main ones. Now, how will they frame a question on this? Example question would be like this. The resistance of a wire at 20 degrees is 50 ohms. And at 30 degrees is, let's say, some 70 ohms. Then they'll say find the resistance at 50 degrees. Then we will say use the formula R is equal to R naught. Remember, R naught is the resistance at 0. So we'll substitute the first one, 50 ohms. R naught we don't know. Alpha we don't know. Change in temperature is 20. The second equation we will use 70 ohms. R naught we don't know. 1 plus alpha we don't know. Temperature difference is 30. So equation 1, equation 2. We will solve these two equations. From here we'll get R naught ka value and alpha ka value. Once we get that, then we will say resistance at 50 degrees will be R naught into 1 plus alpha 50. Substitute the values, you'll get the answer. Clear with this? And direct substitution. So this is the kind of questions I can frame. They'll give you two values at two temperatures and they'll ask you for something else. Yeah, you do get them in CET and bits means sometimes. Great. So let's see some questions on this. Now, one thing, I have a small thing to ask you here. Look at this V drift. The V drift is 1 centimeter per second. Now look at in your house. The distance between the switch and the bulb is almost 1 to 2 meters, right? The distance from the switch to the bulb is 1 to 2 meters or more. So that means from this logic, the moment I press the switch, the electron will take 1 centimeter per second. It should take 200 seconds to reach the bulb. So it should take around 200 seconds delay for the bulb to start working, isn't it? But the moment you switch, the bulb glows. What's wrong with this argument? The speed is 1 centimeter per second. So that means the moment you close the switch, the electron will take 100 to 200 seconds. It's clear. There's no doubt about this part. So technically, the bulb should start working after 100 to 200 seconds. But we know it works immediately. What's happening? Charge flow rate is good. Good क्या होता है? What charge flow rate is good? Yeah, did you guys understand my question? What I'm asking? If you are going so slow, it should take time for your bulb to work. But why the hell the bulb glows up immediately? नहीं रे परम. Yeah, right, Trishi. Anyone else thought of it? Think. I'll give 30 seconds. Yeah, right, Samir. Remember this thing. What did I tell you? Does the battery generate electrons? Where are the electrons? They're already there everywhere in the wire. What does the battery do? Battery simply creates a field everywhere in the wire. So the moment the battery creates field everywhere in the wire, all the electrons in the wire will move at the same time, isn't it? So the way you should imagine a wire, don't think like, the battery is just pushing electrons. Imagine the whole scenario like a conveyor belt. Imagine the whole wire is like a conveyor belt and you have a motor here. The moment you switch on the motor, won't the conveyor belt, whole conveyor belt start moving at the same time? You're getting it? The electric field gets established at a speed of light. So the moment you switch on the battery, the whole conveyor belt will move at the same time. So if you have a bulb here, the electrons near the bulb will reach the bulb immediately. This argument is right. The electron near the battery will take 200 seconds. That is true. But the one who is providing energy to the bulb immediately is the electrons which are pretty close by. Is that making sense? That's the reason you don't see a delay. The battery does not create electrons. Electrons are already there in the wire. It is pushing those electrons like a conveyor belt. That is the way to imagine how does a charge flow in a wire. So it's like a big conveyor belt. They're all sitting there. So the conveyor belt is like electrons just sitting there. The moment you generate this, the entire belt will start moving. Is that analogy making sense? That is the way to think of a wire. Clear. So that's the main idea there. So let's see if you have questions on this. Hmm. Let's get this. These are some theoretical questions on whatever we have done so far. Okay, let's see the first one. So in a wire of cross section of radius r, free electrons travel at velocity v. When the current I flows through the wire, what is the current in another wire of half the radius of the same material? So look at the formula here. So I is equal to NeVd. V. E said same material, so N will be same. E is the electron charge, that also will be same. So I is proportional to area into velocity, right? And area is nothing but pi r square. So that is r square into velocity. So the current is proportional to radius square into velocity. So what did you do? You did half the radius and double the speed. So that will be 1 by 4 into 2. It will become half. Clear? The theoretical questions. What about the second one? This thing I just taught you. The resistivity of a semiconductor decreases with increase of temperature, right? That is right. In a conducting solid, the rate of collision between free electrons and ions increase with increase in temperature. That is also true, but that's not the explanation. C is the answer. Got this? Get the eighth one. Keep going. Okay, let's see the next one. Now be careful here. An insulating pipe of cross section A contains an electrolyte, two types of ions, plus and minus. So we applied a potential difference. So if you see, we have an anode and a cathode. Yeah, it's not important, but just to give an idea. So your cathode is your negative charge, anode is your positive charge. Now you have these ions which are 2e, the positive charge, right? They will go which way? They will go towards the cathode. The electrons which are the negative charge, they will go towards the anode. They're going in the opposite direction. Now, in the beginning, I told you something. The flow of positive charge is called current. So this guy will generate a current I1 in this direction. If the electron goes left side, the current will be this direction, I2. That means even though they're going in the opposite directions, the current will add up in the same direction. So current is I1 plus I2. That will be N. E is 2E. Area is A. Velocity is V by 4 for the positive guy. Plus I2 will be NEAV. So this would be 3 by 2 NEAV. D option. One most common mistake is people subtract them. Be careful with that. So they will move in the opposite direction, but one is positive, one is negative. So the currents will still add up. Is this clear, everyone? Yeah, most of you did get it. Let's see a few more. These all are theoretical stuff. So 11th is a good question. I'll keep all of them in one question. Get it. Why current should still add? Because flow of charge is current and both the currents are flowing in same direction. So we add them, right? If 1 ampere and 2 ampere are flowing in the same direction, so the current is 1 plus 2. So what was the doubt exactly? Let me know if you're confused there. D is the easy part. So what is there? Again, look at this thing. So I is equal to NEAV. Now current is same in both of them because the same current flows. So if you look at this gives you a feeling, A into V is constant. This looks like equation of continuity. So more area, less velocity. So Vp is greater than Vq. Technically speaking, there is no difference. Water is flowing here, electrons are flowing. So it gives you the same feeling like a water ka flow only. It looks like equation of continuity. A1 V1 is equal to A2 V2. Get the equation. It's a good one. Spend some time on it, 1 or 2 minutes. It's a worthy question. Right, Utsa, you got it. Others try. Anyone else? We have one answer from Utsa. Hmm. Show you? Think. So just to give a little idea, so current is I entering here, so it is flowing through this, and then again comes out I. That is the meaning of it. So current I goes there, spreads inside, and then comes out I. So you're sending a current like this, right, Aditi? We have two answers. Anyone else? Okay, let's see. Let's look at each one. Okay. The current at the cross section P equals the current at the cross section Q. True, because the same charge will flow through them. Because the current is charge per time, it does not depend on area. First option is right. The electric field intensity at P is equal to less than Q. Now we know J is equal to sigma E bar, but we know J is equal to I by area. Current is constant, sigma is constant. So E is proportional to area, 1 by area. That means wherever you have more area, you have less field. So P may there is more area, so field is less. So B option is also right. The rate of heat generated per unit time at Q is greater than P. Here we need to know a little discussion. If you take a thin cross section here, dx and dx. I know I still didn't teach you this, but heat per second, you know this thing from school, is equal to I square R. And R is nothing but I square. Resistance is rho dx by area. Current is same, rho is same, thickness is same. So the heat per second is proportional to 1 by area. Means whoever has more area will have less heat produced. So the rate of heat at P at Q is greater than P. That is also right. The number of electrons crossing per unit area. Now we know the current is same in both of them. So current per area AP, right, will be less than current per unit area AQ, because that's simply number of electrons. So D is also right. All four options are right. Do have a look at this. Please ask me if you're confused with any particular option here. That's what makes this question really good. Clear? So think of like this. If you keep sending through this wire, which part of the wire will break first? Let's say you used this wire as a filament for a bulb. You created a bulb ka filament with this. As the bulb is glowing, at which point, at P or Q, at which point will the wire break? Hmm. So you can ask question like this, right, Samyak? Right, Akansha. Right, Utsa. It will break at point Q. Why? Think about this. Point Q may area is small. Since area is small, you get more heat. If you get more heat, your temperature will rise more. If your temperature rises more, you will melt more. If you melt more, you'll become more thin. If you become more thin, you'll get even more heat. So that part will keep getting heated and more and more and more, and eventually it will just break. So in a filament, the weakest spot is the thinnest part of the wire. So if you don't make the filament uniform, if you make a non-uniform wire, the thin spots will become weak spots. And that will actually create issues. Clear with this? So that's the reason, the bulb, if you see these bulbs, they stop working because of that. Next one. If you make a composite wire meaning you joined two different wires. So you made one wire of row 1 and wire of row 2, you joined them. Maybe an aluminum wire and a copper wire, and you're sending current I through them. This is your interface. So you have joined two wires and the current is flowing through them. So composite wire carries current I. Row 1 and row 2 are the resistivities. Now something happens here. Now, to give you a little context, think of like this. Imagine you're going from Mumbai to Pune, and in the beginning you have a beautiful expressway, like 8 lane ka road. And once you reach Pune, suddenly the road becomes 2 lanes. What do you think will happen at this junction? There'll be a big traffic jam, isn't it? The cars will start getting piled up. Same way, if you take two wires, let's say you take a highly conducting wire and you take a wire with, little less conductivity or more resistance, the electrons which are rushing here, suddenly when they try to enter here, there'll be a huge resistance here. So they will slow down. There's like a traffic block here. That means there will be some charge which will accumulate at the interface. So if you join two different wires, so two different materials, there will be a charge on the interface. So basically it gets blocked. Find the charge on the interface. This happens whenever you join wires of different materials. Find the charge on the interface in steady state. I hope you're getting why there will be a charge. Think about it. But I hope that analogy was clear. You're sending traffic from a 8 lane to 2 lane. It happens. And India it is pretty common. They build beautiful roads and then the exit road will be like a 2 lane. One of the best example is our Mumbai mein the express, not expressway, this one. Mumbai Sea Link hai na, Bandra Sea Link. If you ever go on a Bandra Sea Link, you will see it is a 4 lane car road. And the exit is like 2 lanes. So once you're on that link thing, it feels like, oh, you are just cruising. And at the end, then you realize the reality. Now they're making that coastal road. That also will be big. So what all these roads do, right? They simply shift traffic from one place to another. That's it. They don't reduce the traffic. How do we do this? This is a question where it is a little difficult to figure out, but easy to solve. Okay, let's see. Now, when I saw this question for the first time, right, the first feeling is like, what the hell? You're giving current and run, you're asking charge, like what the hell is the question only? So that happens for 10 seconds. And then you calm down and say, okay, matlab, there is a way to do this, so let's figure it out. Then I started asking myself. So this is, see, when you say thinking, right, yahi hota hai. You're asking yourself. You're like, where did I hear about charge till now? Vectors? No. Kinematics? No. NLM? No. Matlab, roughly, right? So mechanics mein to hai hi nahi. The first time you heard the word charge was in Coulomb's law. Sir, can I use Coulomb's law somewhere? I don't know. Then where did you hear about charge next thing? Gauss law. Maybe charge आया था. Capacitor में भी charge आया था. But ये देखिए capacitor तो नहीं लग रहा है. So this must be either from Coulomb's law or some from Gauss law. Then I said current is given. rho is given. Then you start thinking, okay, what can I do with current and rho? There is only one relation between current and rho. J is equal to sigma E, where this is nothing but I by area and sigma is 1 by rho and this is E. And he said, yaar, यहाँ पे तो field है. So I have a field here. मतलब maybe from field I can get the charge. Then again I start thinking, oh, can I maybe use E is equal to KQ by R? But this is not a point charge. That is looking like a disk. So then you start thinking, okay, see, this is what happened. Then you keep thinking, struggling, maybe you don't get an idea there. And then I say, okay, where else do I get this thing? And the charge will be maybe you're non-uniform. I don't know how the charge will induce also. Then I said, is there any other formula with field and charge? And you think like, there is one in Gauss law. Integral E dot dA is equal to Q by epsilon. It gets connected now. That's what's thinking. Suddenly it feels like, oh shit, I know what to do. Karke. And then what you do, we will say, consider a Gaussian surface. Enclosing this. On the left-hand side, the field will be E1. On the right-hand side, the field will be E2. Therefore, the flux will be E2 into area minus E1 into area. Right? This should be equal to Q by epsilon. But we know J is equal to sigma E. So E is equal to J, which is I by area, and that will be rho. Take this and substitute here. So we get I, current is same, by area, and that would be rho 2 minus rho 1 into area is equal to Q by epsilon. Area will cancel. We get Q is equal to I into epsilon by rho 2 minus rho 1. That's your charge. Easy to solve, difficult to figure out. So yeah, so that's what they expect. Now, what made you think that way? That's it. There's nothing you can answer why. Like, this is how your brain works. You are at A, you want to go to B. All you can do is you start asking questions. You keep firing. Okay, what is this? To go to B, what all are there? This one. Then you're firing here. 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 So you're just finding all random directions. And your brain, right, is very smart. What it tries to do, it also fires from back. Maybe you don't realize this, but subconsciously, right, your brain doesn't like, when you're having blanks in the middle, it tries to fill it up. It is also firing randomly. And then it's firing, it is firing, it's firing, it is firing, and then this is firing and firing and just gets connected and like, shit, we know the answer. That's how your thinking works. So that's why I keep telling you, when you do a question and if you don't get an answer on first try, leave it for the day. Try next day for another 2-3 minutes. Most of the times you get it. People don't have that patience. You don't let your brain learn how to connect two things. So you go for an answer immediately or you Google the answer. The moment you do that, your brain lost that ability to think. You lost an opportunity. But we are living in an age of, Swiggy and Zepto, which will give you 10-minute delivery of stuff. Who the hell will wait for a day to get an answer? That is the sad part. And then people ask like, sir, exam mein mujhe ideas nahi aata hai. I get stuck. I don't get an idea how to start. I keep, I see the question after the exam, I get it. All that happens because you lost your ability to think. You got used to fast food. You don't enjoy the taste of a carrot anymore. When was the last time you ate a carrot or an apple and felt like, wow, what a taste? You should do that. You know what you can do? Don't eat food for 2 days. Do fasting, only water fast. Don't eat any food, only water for 2 days. And then, trust me, eat a carrot and you'll feel like, what a taste. You will even enjoy drinking water with salt. If you put little salt in the water and drink, you'll feel like, wow, what a taste for the water. So that is the thing. One day I did an experiment. I used to do last, like, I think my best was 60 hours without eating. And still working. Okay. You don't die. Lagta hai aisa, you don't eat nothing. Your body has enough fat to survive for like 30 days. You must have done this thing, na? This, Jains do that fasting for 7 to 9 days. Kuch to bolte hai usko. They do it for 9 days. Jain monks also do fasting for 30 days, but just with water and salt. So acidity kuch nahi hota hai, right? Your body actually starts healing. Once the body realizes this guy is not eating, first thing it just stops all the acid production. Your stomach becomes like gone, shutdown mode. It goes for rest, and it will thank you. It's just like, good boss, I got to finally one day rest, not to do anything. Morning, evening, I am just working for you. Finally, I got a holiday for myself. So yeah. Next thing, combination of resistors. Think about what I said. You get a question. That's what I keep saying. Don't run behind between too many questions. Do less, but try to figure out most of it on your own. That's what is needed for advance, because exam there will be no one to help you out. Why do you fast for 60 hours? I didn't. I wanted to see actually how long can I stay. Plan was for 72, then I had to break at 60 because I was going for a class and I started feeling dizzy. I said, like, I got scared and I drank. I got scared actually, nothing much. I thought I might fall down somewhere on the road, and then people think these guys are drunkard and no one will even take me to hospital. So I thought, why to take a risk? So that is the thing. Huh? If you are going to fall on a road, you have to dress well. Then people will care about you. If you just dress normally like a jeans and t-shirt, people will think these guys are drunkard. The dressing matters. Anyways, series. This stuff, we already done this multiple times. Same current and same branch. So I'll just rush through this. R1, R2, you can replace them with one resistor R equivalent. They have the same current I. Then you can add V1 by V2 is equal to R1 by R2. Parallel. So till now, whatever I showed you, right, all this was the theoretical part of it. Kind of neglected part. People think current means all circuits and all, but what we did so far was more important. And I'll show you questions based on this. So here, all the techniques I taught you, series, parallel, Wheatstone, nodal analysis, symmetry, junction law, everything works, right? So yeah. Fasting causes significant hair reduction. Yeah, that's why you should take multivitamins. Oh yeah, I did all these nonsense experiments. IIT में we used to do even more weird things. How many days can you stay without eating and sleeping? I think mine was 32 hours, and then I fell asleep. And my idiot friends used to bring KFC, pizzas, and eat in front of me. That was even more hopeless. That's what we do, right? If someone is fasting, you go with the food and you dance in front of them. Anyways, so next thing, Wheatstone bridge. So all the circuit stuff, what we're doing will look similar, but yeah, we have few variations where like they're really good. We'll see that also. If R1 by R3 is equal to R2 by R4, then R pi can be removed. How many times you have seen this already by now? We saw this in heat transfer conduction. Then we saw in Poiseuille's equation, viscosity, capacitors, current electricity. Somewhere else also we saw this thing. Springs in series, springs in parallel. You don't have a Wheatstone bridge, but you have series and parallel. 5 times you have seen this so far. Then we also have an extended Wheatstone bridge. You can even, have something like this. Basically, you can fold this and this becomes an extended bridge. So R1, R2, R3, R4, R5, R6, R7, R8, R9. So if all that vertical ratios are same, you can remove that middle resistors. So yeah, maybe I'll just, you got that anyway. I'll put this thing. There are too many resistors. If R1 by R2 is R3 by R4 is to R5 by R6 is same, then R7, R8 can be removed. Clear this? Let's see a question on this. Ratio is not same, then you go back to the junction law, Kirchhoff's law, remember? That's your final technique. हमने किया ना equation याद है C2 C3 C which was not balancing out. We got a cuboid here. This is A, this is B, and this is C. This is phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. So if you connect the battery between 1 and 2, 3 and 4, and 5 and 6, you can connect battery in different phases. Find the ratio of resistance R12, R34, R56. Meaning if you put the battery between 1 and 2, what is the resistance? 3 and 4 resistance, 5 and 6 resistance. Second thing, we got a cylinder whose resistances are. Whose radius is A. Then what you did, you melted this, you melted the cylinder and you recast into an equilateral triangle, a rod of an equilateral triangle base, a Toblerone. Ever seen a Toblerone? It looks like this. So you made a rod with an equilateral cross section. Whose side is also A. Find the new resistance. So initially resistance was R. You melted that, you made a Toblerone. So what will be the resistance of this thing? There, get them. Straightforward questions. Yeah, right, Samyak got the first one. Keep going, everyone should try. Param, एक बार check करो. I think you messed up that B and C. C and 4, I guess you're messing up. Aditi, you also messed up that thing. Right, Param? B and C देखो ना, Aditi. Okay, let's see the first one. See, one thing when you do between 1 and 2, ask yourself, what is L? L is the length along the current flow. What is A? Area perpendicular to the current flow. So when you say R12, length will be, current is going from 1 to 2, A, area is BC. What is R34? Rho, length will be C by AB. R56, rho B by AC. Multiply and divide by A, multiply and divide by C, multiply and divide by B. If you do this, we get ratio a square is to c square is to b square. There's actually a better way to do this. Resistance is equal to rho L by area, multiply and divide by length. Then this will become rho into L square by volume. So R is proportional to L square. This is even faster because for no matter how you connect it, the volume will remain same. So this is faster. Is the logic making sense? R is proportional to L square because no matter how you connect, volume will remain same. So same story here also. If you see here, when you melt this thing, what remains same? The volume remains same. So what we can do, R is equal to rho length by area. Now here I know area, I don't know length. So multiply and divide by area. This will be rho into volume by area square. So resistance is proportional to 1 by area square. So if lengths are given, use length. If areas are given, use area. So the R by R new, what was the initial area? Pi a square ka whole square, it is area ka square, into 1 by, this is an equilateral triangle. So what is the area? Half base into height. Half base height is root 3a by 2 ka square. A square will cancel. This will be 3. That will be 4 square, 16. Pi square. Yeah. And then we get R new is 16 pi square by 3. Check. Clear with this? So the idea here is when you melt something, volume remains constant. Actually, from there you can find the ratio of length and do all that, but this is faster. You just modify the formula only. You want to find R13, you can't find. The currents will not go in a proper way, right? To start curving. So कुछ नहीं कर सकते. All got this? Be careful, it is proportional to area square. 1 by area square, not 1 by area. Take a break. Come back by 9:45. We'll continue from here. We'll do more on this now.
Sir,
हाँ देते.
yeah, also I just wanted to say कि आजकल I've been asking to keep my cam off शुरू में. It's because वो maths वाला जो class है, it overlaps. That's why I just wanted
चलेगा, it is okay. No problem.
to.
Happens. Yeah, let's go ahead. Let's solve more. Yeah, let's solve this. Each segment is a resistor R. Find RAB. It's your favorite Diwali star. You know all the tricks, the techniques we learned in capacitors. All those are valid. Opening the nodes, the folding the circuit, all that is valid. You should definitely refer to the capacitor notes in case you forgot. Okay, let's see. So first thing you can clearly see here, this thing has both bisector symmetry and axial symmetry. So if you look at this line here, this is your bisector symmetry. You can open the nodes along this line. You can refer to the capacitors there. That means if you draw the picture, this is how it would look. So this node in the middle, you can open it up. This is how it looks, everyone. So you can join these two. Make sense? You can just open that junction there, and this is how the circuit looks. Now look at this carefully. Look at this triangle here. This guy and this guy are in series. These two red ones which I'm marking. So that will be RR, 2R. They're in series. That 2R and this R are in parallel. So this whole triangle here is 2R by 3. Similarly, this whole triangle here is 2R by 3. And this one is R and R, 2R, R and R, 2R. 2R and R is R parallel. R and R is again R by 2. So this middle section here is R by 2. Same logic here. This guy was 2R by 3. This middle one is R by 2. You can fold it, but okay, I'll leave it like this. This is 2R by 3. Now if I redraw the circuit, this thing actually looks like this. Resistor, resistor, resistor. So this is B, this is A, this is this 2R by 3. This is that middle one, R by 2. This is the 2R by 3. And this is the middle. Remember, there are two resistors here in the middle. That is your R and R. And 2R by 3, R by 2, and 2R by 3. Now this simply becomes series and parallel. Yeah, we'll get 22 R by 35. Right, Anvita? Who else got it? Samyak, right? Got it. Arya got it. Clear with this? So once you remove that node in the middle, suddenly the whole thing becomes doable. Any doubts on this, please ask me. Yeah. Let's see one more. So find the resistance between RAD, RBC. Two different questions. Meaning you're connecting the battery between these two guys, A and D. These are the values of the resistance. Huh? This is 2 ohms, this is 1 ohm, 1 ohm, 2 ohm, 1 ohm, 1, 1, 1, and 2. So those are the values of the resistors. So find the resistance between A and D. If you put the battery between them, second question, put the battery between B and C, the green ones. So depending on where you connect the battery, the circuit will change. Others, do keep your cams on. Okay, RAD something. Let's see. Okay, let's see the first part. So you want between A and D. So let's do that thing first. So we are doing between A and D. Look at this. So you're talking between A and D. So if I drop a line here, if you see, this is an axial symmetry. Be careful, just because the line is vertical doesn't mean bisector. Is the line of symmetry passing through the terminals or dividing the terminals? It is passing through the terminals. This is an axial symmetry. That means the left and right are identical. So point B and point C will have same potential. Similarly, point E and point F have same potential because left and right are identical. B and C have same potential. E and F have same potential. Now, if 2 points have same potential, any resistor between them can be removed. Right? So if you can remove the resistor between them, this is what will happen. So between E and F, you remove this guy. So there, this thing will vanish. Similarly, this will vanish. There, now it is done. So you will get it easily now. So since B and C ka potential is same, any resistor between them can be removed. E and F ka potential is same. Any resistor can be removed. You can clearly see this 1, 2, 1 are in series. These 4 are in series. So if you try to draw the circuit, this is how it looks. So we have one resistor here, one resistor in the middle, and one resistor here, and this is D. This is 4, this is 1, and this is 4. This is 2, sorry. 4, 4 parallel, 2, 2, 2 parallel. So RAD is equal to 1. Is that clear, everyone, what I did? So in an actual symmetry, right, the left and right are identical. Matlab, whatever happens on the left, same thing happens on the right. So the potential must be same. What about the other one? Now we are doing for B and C. Meaning here and here. Now again, if you see, now this is a bisector symmetry. See, it is dividing the terminals. That is how you decide. If the two terminals are on either side of the line, it is a bisector. If they're on the same line, like then it is a this thing. So now bisector symmetry is what? This is equipotential. So all points on this line are midpoints. So they'll have same potential. Therefore, A and D have same potential. That means anything between A and D can be removed. So this point and this point have same potential. Now, if you draw the picture, you can remove this guy 2 in the middle. Now, once you do that, your life becomes pretty easy and straightforward. These two are in series, this and this are in parallel. These two are in series, this and that are in parallel, and this is in parallel. Everything becomes series parallel. You can clearly see that. I remember the answer. This thing is 7 by 12. You can remember this thing. Check it out. Once you remove that AD, circuit becomes pretty easy to solve. So these two are in series. That 2 and 1 are in parallel. This whole thing is in series. The upper one and this one are in parallel, and this is in parallel. The whole thing becomes series parallel. So you just have to be careful. If you see removing 1 or 2, suddenly things will change a lot. Any doubts on this? Can you explain AD? Which part, Vedika? You're asking how did I remove it?
Yes, sir.
In a bisector symmetry means what? All these points are midpoints, isn't it?
Yeah.
So if all are midpoints, then uska potential will be V by 2. So if all have same potential, that means if you connect anything between them, the resistor mein current won't flow. So that AD ka resistor useless tha. If current is not flowing, you can remove it. So you're done. Okay, this thing na, once revise this everyone. Symmetries mein we did it here. Yeah. Symmetrical circuit bisector. यहाँ पे लिखा था. All nodes on the same line have same. All the nodes on the line have same potential. The bisector line is equipotential. So because those all are midpoints, you'll have half of the potential V by 2 kind of thing. All got this? Yeah. Great. Now let's see something different in this, but it is still series parallel. Let's say we have a concentric shells. We have done something like this in heat transfer. The space between them is filled with a resistor material. Let's say this is rho. So the inner shell is connected to a battery of voltage V, and this is grounded. The outer shell is also grounded. Meaning, what will be the potential now? So this inner shell will have a potential V, and the outer shell will have a zero potential. The inner radius is A, and the outer radius is 2A. This is a conducting shell, conducting concentric shells filled with a medium. Concentric. conducting shells with a medium. And this medium resistivity rho is also not constant, which is rho naught into x. I am messing up everything. X is 2a, 2a. So this rho is your resistivity. So as you go outside, it is becoming more and more resistance. Rho naught is some constant. This will be a good paragraph question. And x is the distance from center. Is the picture making sense, everyone? So we took two concentric shells, and in the middle, you filled it with a medium of rho naught x. First thing, find R equivalent. So what is the resistance between the two shells? Find current. Find J of x. J is the current density. Find E of x. That is the electric field as function of x. Find potential as function of x. Let's get these three. So the inner shell has potential V and the outer shell has potential 0. That is the meaning of the battery. I hope the battery is not confusing. I can just put V here and 0 here if that's confusing. So the battery will maintain a potential inside. So inner shell has potential V. So current will flow how? Will flow from inside to outside. And if you think this is looking new, no, it is not. You have done this in heat transfer. Equation याद है? Exact same question देखो. Inside temperature is 2T naught, outside temperature is T naught. K is the thermal conductivity, K naught X. Solid sphere with a cavity, inner surface and outside temperature is R thermal, dQ by dt, dt by dx. X is distance from center. The question is quite similar. In place of conductivity, I gave you resistivity. And that's what I keep telling you. Things are connected. It's not like when you learn something, it is always useful somewhere else. Give it a try. Get the whole thing. Yeah, that looks right, Samyak. Arya looks right. So try. I think the most important one is the potential. Yeah, I think most of you getting the resistance part right. I'll give another 30, 40 seconds. I'll show you the resistance. If you got the resistance, everything will fall in place. Let's see. So at a distance x, take a thin shell. thickness dx. So for this thin shell, how is the current flowing? Current is flowing radially. So for this thin shell, what is the resistance dr? Rho. Length, what is the length? Dx. So rho is rho naught x. I'll just write the formula when you rho dx by area. Area is 4 pi x square. So length is the L is the length along the current flow. So current is going along dx, and the area is 4 pi x square, the whole surface. And rho is nothing but rho naught x. So rho naught x dx by 4 pi x square. This is the resistance of the thin shell. So you want the whole resistance R equivalent. That will be rho naught by 4 pi integral dx by x. Limits will go from a to 2a. That will be ln 2. So rho naught by 4 pi ln 2. That's your resistance, everyone. Once you got the resistance, current is simply voltage by R equivalent. One step, you'll get the answer. Once you got the current, current density is simply current by area. What is area? 4 pi x square. J का value भी आ गया. Once we got J is equal to sigma E. Therefore, electric field is nothing but J by sigma, which is J into rho. There you got everything. So J is I by 4 pi x square. And rho is rho naught x. So we get electric field inside is equal to current, which is actually constant, rho naught by 4 pi x. So this field is actually proportional to 1 by x. They can play like this. Please have a look at this. So this is the main thing. Once you got the resistance, everything will come back to back. Now, what else I'm asking you? Find the potential. How do you do that? So at A, potential was V naught. At 2A, potential was 0. What about the potential somewhere in the middle? Okay. So check your answer na Samyak. If you put x is equal to A, I should get V, and x is equal to 2A, I should get 0. I think you're getting it. E of x is V by epsilon to nay, na? Utsa, check karo. If you put x is equal to A, you're not getting you're not getting V. Vx is 0. Matlab potential everywhere is 0. God. How do you do this? How do you find the potential? There are two ways you can handle this. One, when you took the thin shell, the current was flowing I. So the small potential difference dV is equal to minus I into dr. Why minus? Because the potential decreases in the direction of the current. This is the potential difference across the thin shell. I is constant. And what is dr? Dr is this value, everyone. Dr is rho naught dx by 4 pi x. That is your dr. So we get dV is equal to minus I rho naught dx by 4 pi x. Integrate this. So dV minus I rho naught, I ka value we already know, integral dx by x. Limits will go from A to x. At A, potential is V, and this is V of x. Or you can take two-way also, that also works. If you can take two-way, then this will be 0. Then this will be Vx is equal to minus I rho naught by 4 pi ln x by 2a. You can bring I ka value and substitute here. It works. Or there is an alternate way. Electrostatics. VA minus VB is equal to minus integral E bar dot dr. Remember this? A भी कर सकते हो. Since you know the electric field from here, you can integrate and get it. That also works. All clear with this? Yeah. Let's see one more. So we got a part of a cylindrical piece. This is your radius R. This was distance D. This was length L. This was rho. The battery is connected between this point A and B. The top view looks like this. If you see this from the top view, this is looks like an arc which has a thickness. This angle was theta. This was D and this was R. The battery was connected between this point and this point. Do one thing, take it as A, because R we'll use for resistance. Are you getting how is the picture? It's
So we
like
are already using A.
they're already using A. वो just terminal है रे वो, ठीक है? I did now 1 and 2. Terminal 2 and terminal 1. Happy. That is the battery there. Get it. Is everyone clear how the picture is looking? It is an arc with a height. Find R equivalent. Find current. Find drift velocity as function of x. N is the number of electrons per unit volume. X is the distance from the center. Meaning if the electrons are moving inside, how will the drift velocity matter as a function of x? First, that's R equivalent. That's the main thing here. How will you choose an element here? How do I tell what this thing looks like? It's like you took a block and you bent it, kind of like. The picture was clear though. How will you choose an element? That's the main important thing, how to choose an element. Now, if you try to choose an element like this, so let me show you how. See, you cannot choose an element like this. This won't work. Because if you choose an element like this, if you see the element ka size itself is weird, right? There is no area defined there. You cannot take an element like this. So this thing itself is changing. So how we choose an element here? We take thin strips. We take a thin strip here. Are you guys able to see how it is? So at a distance x from the center, we will take a thin dx. So for this thin strip, this will be the area, the green one which I'm shading. That area will be LDX. Basically, current is going to come out of this strip. Current will come from here. This is how the current is flowing out from that thin strip. And what is the length of the strip? This length of the strip will be x and theta. So here the length of the strip will be x theta. So this current is flowing along the strip, everyone, like this. Are you guys able to see the strip? What is the resistance of this thin strip? This is the resistance of thin strip. Rho length x theta by area LDX. This is the resistance of the thin strip. You have to be careful, dx is in the denominator. Now this is where people goof up. Now you try to integrate this. You can't do this. Understand the meaning of this. All the strips are in series or parallel. If I draw one more strip like this, what do they have same? They have same potential difference, isn't it? All the strips are in parallel because they have same potential difference. Therefore, if all the strips are in parallel, what is the formula? 1 by R equivalent is sigma 1 by Ri. That means 1 by R equivalent is integral 1 by dr. Be careful, you're not supposed to integrate dr. The meaning of integral is summation. So this is the summation of 1 by dr elements, isn't it? So if you integrate this 1 by dr, now you will get L dx by rho theta x. And the limits will go from a to a plus d. So this will give you 1 by R equivalent is equal to L by rho theta ln a plus d by a. Reverse this. You get rho theta by L into ln 1 plus d by a. That's your resistance, everyone. Have a look at this. The most thing is that figuring out that this would be actually all in parallel. You're not supposed to integrate dr. That's a mistake. Because they're in parallel, you're supposed to integrate 1 by dr. Then you can ask me, sir, previous question, why did we integrate? Because previous question, all the shells are in series. And series, you can directly do integral dr. That's the reason I took one problem with series and one problem with parallel, so that we can cover both the variations. Any doubts on this, please ask me. It's a pretty good one. That's how you choose elements and get it. Because where is the battery, Akanksha? Left and right, na? So isn't the potential difference same then? This is 1, this is 2. This is where the battery is, isn't it? So this was 0.1 and this was 0.2. Haan, bolo.
Sir, is V given in the question?
V given in the question. Yes, I'm supposed to give that in the question. I forgot. Let the voltage of the battery be V. लिख लेना कहीं पे तो voltage V. You can take it as E. The picture is already big, so I didn't draw. And then what is the current? That is the easiest one. Voltage by R equivalent. डाल देना current आ जाएगा. Clear with this? Now the main part. How do you find the drift velocity? How do you find the speed of the electron at a distance x from the center? Look at this. This actually leads to something really interesting. So when you take this thin strip, right? We already got dr, that is the resistance of this thin strip. How much was that? Dr was this guy, rho x theta by L dx. Okay. This is the resistance of the thin strip. So on this thin strip, how much current will flow? In this thin strip, this is the I in the strip. So current in the thin strip is the voltage, which is the EMF E by dr. That will give me E L dx by rho x theta. This is the current flowing in the thin strip. And we know current is nothing but N E area V drift. Yeah, the formula. So in that particular thin strip, the current is I, and that is equal to NE V drift. So current is EMF length dx by rho x theta. This is N, which is given. E is the charge, and what is the area? Area is this strip. This area is L dx. So area will be L dx into V drift. L dx will cancel on both the sides. We get V drift is equal to E by rho x theta N E. And if you see, this is proportional to 1 by x. That means, look at this thing, interestingly. The farther the radius, the slower the electrons go. That means electrons on the outer edge are going slower compared to the electrons on the inside edge. All the electrons are not reaching the thing at the same time. Is the idea clear, everyone? So I found current in thin strip, and then I said I is equal to NeVd. That's how you get the drift velocity. You can't take the current in the whole thing, because at every point you don't have same amount of current. Every strip will have different currents, so they'll have different velocities. Any doubts on this? Here. Rho is the resistivity, U2 conductivity. Now, here you can do something even more interesting. I didn't ask you, but there is one more level to the problem. Listen, I'll tell you what happens here. There is something called a transverse voltage. This happens whenever you take conductors which are curved. Now, this becomes mechanics. So you see what happens. So when you have this curve thing, and just now we proved these electrons are going in a circle, right, with the drift velocity. This was theta. Now, if you choose an electron here, and this electron is going with some velocity v, now because you're going in a curve, what do you think will happen? There will be a centrifugal force, mv square by x, where x is this distance. The electrons experience centrifugal force. This is the centrifugal force on electrons. And because of this, what will happen? The electrons will start accumulating on the outer edge. Due to this, charges are induced on inner and outer surface. Because it is a curve. Why didn't it happen previously? Because when you're going in a straight line, you don't have this problem. Generally happens, imagine, when you're going on a curved road, the traffic tries to go away from that. So this is how the picture will become, everyone. So if you look at this curve, because the electrons are going out, this side will start becoming negative charge. The electrons are pushed outside, and this is becoming positive charge. So this negative and positive charges will create a field. Now this field is different from J is equal to sigma ka field. Both are different. We get a field. This E is called a transverse field. Transverse, basically along the radial direction. So this is the field along the radial direction. Don't get confused this with the other field which we have. I'll show you that also. There is one more field which is coming in this direction. This is E, tangential. This comes from J is equal to sigma E. So there are two fields here. There's one radial field and there's a tangential field. This is a tangential field. This is coming because of the battery. So in this, there are two different fields. So this is the E transverse. Now, because of this E transverse, what will happen? Now, this guy will become positive here, and this will become negative here. So these induced charges will create a counter field. They are not happy, electrons going there. And in steady state, after some time, eventually, right, they will reach a steady state. You have accumulated enough charges. So we get E into E, the electric force is equal to mv drift square by x. So from here, we get electric field is equal to m into v drift square. What is v drift? E by rho x theta ne. E by rho x theta ne cos square by x. So the electric field E transverse would be m e square by rho square theta square n square e square x cube. So whatever. So this is something like some constant into 1 by x cube. So this is the field which is proportional to 1 by x cube. And because of this field, you actually get a potential difference. So we can write this E transverse is equal to k by x cube. So that k is that constant. So this is that k. Then we can write the potential difference V plus minus V minus. This is called as transverse voltage. So this is the potential difference across the what do you call it? The inner and the outer one. So there is a name for this. It's called transverse voltage. This is given by minus integral E transverse dot dr. That would be integral k by x cube dx. Limits will go from a to a plus t. That would be k by x power minus 3 plus 1 by minus 3 plus 1. That's minus 2. So that will be k by 2 x square. Limits will go from a to a plus 2. That's k by 2 by 1 by a plus t whole cube. I think limits I wrote wrong. This is a and this is a plus t because plus is inside. This would be 1 by a square by 1 by a plus t whole square. This is the voltage difference between the inside and the outside one. Is this clear, everyone? You got R equivalent, you got current, from there you got drift velocity, then you used circular motion, from there we got centrifugal force, from there we said there is an electric field, and then we use an electric field to find potential difference. So this is called transverse voltage. This is how you can play around with the equation. This is the kind of things you can expect in advance. Clear with this? It's a good question. Definitely check it out. So the first thing is you need to realize it's in parallel. Then from there we can go ahead. So that's a bit about it. So next class when we catch up, we'll continue from here. We will see more now. Kirchhoff's junction law. I will show you more circuits. We will do more variations of it. Next class will be quite important in terms of circuits. And yeah, I think we'll spend next full class based on circuits only. And then we will maybe time permits. We'll start off with RC circuits. What happens if we put a resistor and a capacitor together? That's the next part. Okay, we will continue from here on Tuesday. So please start solving capacitors like I keep saying. Finish it off. Don't delay it anymore. And there's a test online tomorrow, so make sure to give it. So any doubts, anything else, please stay back and ask, or else you're free to leave. So I'll see you guys again on Tuesday.